Welcome to the Deep Dive, the place where we take a massive stack of complex source material, filter it down, and turn it into knowledge that you can actually use. Today, we are looking at a machine that has, well, it's baffled observers for over a century now. It's a vessel that looks like it belongs in some kind of sci-fi future, yet it operates on physics that were being developed way back in the late 1800s. We are talking about the hydrofoil.
It really is. It's perhaps the most elegant piece of engineering you'll find operating on water today. And our sources, they just captured its essence perfectly.
How so?
They called it the boats that learned to fly. And our mission today is really a full spectrum analysis of that idea.
Okay, so a deep dive. What are we covering?
We're going to unpack the counterintuitive physics that lets a heavy hull just levitate. We'll trace its surprising history, from the drawing boards of Victorian-era engineers all the way to Cold War military assets.
Yeah, and then bring it to the present.
Exactly. And ultimately, we need to understand why these flying boats are not just some novelty. They're predicted to become the absolute backbone of 21st century coastal mobility by, 2035?
That's a huge claim. Okay, let's unpack this, and I think a good place to start is with the source material's opening riddle.
I love this riddle.
It's great. When you watch one of these things move, especially one of the modern racing yachts or, the silent electric commuters, it just achieves these incredible speeds and this remarkable smoothness. And the description offered is a boat with no wheels, no aerial propulsion, yet it flies.
Right.
And that forces you to confront this core question, which is, why does this boat even need water if it seems to be spending all its time and energy trying to escape it?
That riddle just captures the aquatic paradox so beautifully for you, the listener. It looks like it's completely defying the rules of marine architecture,
Was.
It enters this state of near levitation where the main hull is completely separated from the turbulent surface of the water.
And the visual is just stunning.
Oh, it is. As our sources note, it really does look like the midpoint between a spacecraft and a high-performance surfboard.
Yeah.
But the magic, the key to the entire design, it's all operating on this elegant physical principle borrowed straight from aviation.
But amplified.
Amplified dramatically by the density of the liquid it's moving through.
So we have to define that core component, the thing responsible for this aquatic levitation. We're talking about the hydrofoils themselves.
Yes, the underwater wings.
They're essentially these highly specialized wings mounted right there beneath the hull, and they're shaped, for all intents and purposes, exactly like an airplane wing.
Exactly like one.
Yeah.
But they're designed to cut through water, which, as we know, is orders of magnitude denser than air.
And that's the key, isn't it? That density difference?
That is the secret sauce.
Right.
Water is, roughly 800 times denser than air? This incredible resistance is usually a curse for boats, right? It slows them down, it makes them horribly inefficient.
Constant battle.
But the hydrofoil brilliantly turns that resistance into a massive advantage. You need much, much smaller wings to lift the same amount of weight, and you can generate these enormous forces very, very quickly.
And the immediate observable benefit is what makes the technology so transformative. Once the vessel gets up to speed and that hull rises, the primary nemesis of all maritime transport, friction or water resistance, is practically eliminated. The sources say it literally falls off a cliff.
And that reduction is the core mechanical advantage. If you imagine traditional displacement boats, they're just plowing through the water like bulldozers.
Creating huge wakes, huge resistance.
Enormous wakes, yeah. They're just pushing water out of the way. The hydrofoil, in sharp contrast, travels more like a skater gliding on fresh, hard ice.
That's a great analogy.
And that reduced friction allows for sustained higher speeds. We're talking routinely 30 to 60, even more, miles per hour. It delivers an extraordinarily smooth ride and, most critically in our current era, results in phenomenal fuel and energy efficiency.
Let's circle back to that riddle for a second, just to define the hydrofoil by what it is not.
Okay.
When we say no wheels, that part's pretty clear. It's strictly a water machine, it's not amphibious. But the crucial differentiator is that phrase, no aerial propulsion.
This point is absolutely essential to separate it from its high-speed cousins, like the hovercraft or the seaplane. The lift is generated entirely by hydrodynamics.
So the science of fluid motion through water.
Exactly. We are not talking about massive jet turbines or those ducted fans or the complex air cushions on a hovercraft that are pushing these voluminous amounts of air downward. The entire energy exchange, the magic, happens completely underwater.
Which means the actual propulsion system tends to be, well, pretty conventional, just highly efficient.
Pretty much. It's usually standard underwater propellers, maybe water jets, or increasingly now in the 21st century, these super quiet electric motors coupled with highly optimized gearboxes.
So the paradox remains.
It does. The hydrofoil behaves like an aircraft. It achieves lift, it maintains flight characteristics, but it lives entirely in the water. It uses physics that's, beautifully old school, but applies it with a futuristic level of precision.
That sets the foundation perfectly. Let's move into a deep dive on that core physics in part 2. We really need to understand the mechanics of takeoff, how a boat actually generates lift while it's still underwater.
Right.
Our source material calls this segment "The Ocean Takes Flight," which really hints at the counterintuitive nature of the whole process.
And this is where we satisfy the learner's desire for that true aha moment. We have to start with the function of the foil itself. Again, shaped like an airplane wing, but operating in a medium water that is 800 times denser.
Which allows for that rapid force generation.
It does, but it also demands extremely high precision in the engineering and especially today in the control systems.
So here's the big question. How does a tiny underwater wing support, say, 200 tons of boat? Does it all come down to Bernoulli's principle, that famous pressure dance between the top and bottom of the wing?
Bernoulli is definitely a key player, a huge player, but maybe not the only one.
Okay.
When we look at that classic teardrop wing shape, the airfoil, or in this context, the hydrofoil, it's designed to do one thing: manipulate water flow. As the foil moves, the water is forced to travel faster over that curved, longer upper surface.
Right, a longer path means higher speed.
Exactly. And according to Daniel Bernoulli, who figured this out way back in the 18th century, the faster a fluid moves, the lower its internal pressure.
So you get a pressure drop above the foil, a low pressure zone.
Precisely. You get lower pressure that's almost sucking the foil upward from above, while at the same time, the water flowing slower beneath a flatter bottom surface creates a higher pressure zone that's pushing up from below.
And that's the lift.
That pressure imbalance, or differential, is a critical component of lift. It's this choreographed duet of fluid speed and pressure that pushes the entire boat upward.
But if Bernoulli's principle requires that very specific curved shape, what about foils that are flatter? Our sources point to a second, and maybe equally important, mechanism, Newton's third law.
Ah, yes, Newton. He's the essential workhorse here, especially during those critical moments of transition and at very high speed. The hydrofoil isn't mounted perfectly flat horizontally. It's always set at a slight upward tilt.
And that's called the angle of attack.
That's the one. By tilting it, the foil acts like a simple wedge, physically forcing that dense stream of water downward.
And since Newton's third law famously states that for every action there's an equal and opposite reaction.
The action of pushing all that water downward results in a powerful, equal, and opposite reaction force pushing the boat straight up. A much more direct, you could say brute force, form of lift.
So Bernoulli is the finesse, and Newton is the force.
That's a great way to put it. Newton's law contributes significantly to the total lift, especially in some of the heavier or older foil designs.
Okay, so the combination of these two principles, Bernoulli and Newton, is summarized in what's called the lift equation. And this explains why the moment of takeoff is so dramatic. Lift grows with velocity squared.
Yes.
What does that quadratic relationship mean in practical terms? For you, the person standing on the deck, what does that feel like?
It means everything. It's the entire reason the hydrofoil doesn't just sort of gradually float up.
It's not a gentle process.
Not at all. Think about it. If you double your speed, you don't just double your lift, you quadruple it.
Wow.
And if you triple your speed, you increase the lift by 9 times. So you're chugging along slowly, using enormous amounts of power just to overcome that initial displacement drag. But the moment you hit that critical takeoff speed, the point where the square of the velocity just tips the balance, the lift skyrockets. It overcomes the total hull weight in this aggressive, rapid motion.
It sounds almost exponential. That must make the transition phase, from being a boat to being a flyer, incredibly challenging to manage, even for modern computers.
Oh, it is. It's the most unstable, the most nerve-wracking phase of the whole operation, both historically for pilots and technologically for the software today.
So let's walk through the 3 phases of operation to see why. Phase 1 is the hull-borne mode, low speed.
Right. You're just acting like a typical boat. Drag is absolutely massive. You've got friction from the hull. You're forming a wake. There's wave-making resistance. You are burning a huge amount of energy just pushing water out of the way. It's the less efficient phase by far.
And then you hit that unstable second phase, the transition, or partial lift.
As that velocity squared term starts to really kick in, The lift becomes significant enough to start fighting gravity. The hull begins to rise, and the wetted area, that's the amount of the boat still touching the water, it shrinks sharply.
So drag starts to fall off here.
It falls rapidly. But the instability is immense. The center of gravity and the center of lift are shifting dramatically, often requiring the pilot or the software to perform these constant, subtle adjustments to the pitch.
The nose angle.
Right, and the trim, just to prevent the vessel from nosediving or starting to porpoise.
And then finally, the moment of victory, phase 3, foil-borne mode, true flight.
This is the entire point. This is the definition of the hydrofoil. The hull is completely out of the water. Only the slender, specialized foils and the propulsion components are still submerged.
And the wave drag.
Gone. Wave drag, which is the single largest energy consumer for traditional hulls, is now virtually zero. Hull friction disappears entirely. The resulting efficiency gain is it's astonishing.
Yeah.
You're achieving an 80–90% reduction in total drag compared to where you started in that displacement mode.
So that reduction is the whole story, the entire engineering imperative.
Absolutely. The whole design is built around that single goal.
That reduction is the core story here. Hydrofoils are really defined by how cleverly they outsmart drag, which is the universal enemy in all fluid dynamics. If we break it down, what are the 3 traditional forms of drag they specifically defeat, and how?
Okay, so we can categorize the enemy into 3 main types. The first, and most obvious, is parasitic drag. It's often just called skin friction.
Literally the water rubbing against the boat.
Exactly. It's just the water rubbing against the boat's surfaces. Hydrofoils defeat this by minimizing the wetted area down to just those tiny, slender foil surfaces. Less surface area means less friction. It's simple, elegant, and incredibly effective.
The second type is induced drag, that's the price we pay for creating lift, right? The so-called lift penalty.
It is. Induced drag is caused by the laws of fluid dynamics just trying to equalize pressure. At the very tips of the foils, you have high-pressure water from the bottom trying to leak around the tip to get to the low-pressure top side.
And that creates turbulence.
It creates energy-sapping vortices, these little mini whirlpools. Hydrofoils manage this by using very long, slender foils, what engineers call a high aspect ratio.
So think of the wings on a high-performance glider.
Perfect analogy. While longer foils can sometimes reduce maneuverability a little, they are fundamentally more efficient at reducing those powerful tip vortices and minimizing the energy leakage that's caused by generating lift.
And the greatest victory, which we touched on but really bears repeating, is the complete elimination of wave drag.
Wave drag is all the power that's lost when a traditional hull pushes water aside, creating that classic V-shaped wake you see behind a ship.
That wake is just wasted energy.
It's pure wasted energy. Hydrofoils eliminate this entirely the moment the hull is airborne, because the boat is no longer displacing a large volume of water. It's simply slicing through it with minimal disturbance. This elimination of wave drag is the massive gain. It's the defining victory in the entire drag battle.
So the conclusion is simple.
Hydrofoils win the drag battle by surgically removing the hull, the biggest, clumsiest drag contributor, from the equation entirely.
But once you lift a massive boat out of the water and balance it on these tiny, high aspect ratio wings, you introduce some massive stability challenges. If your stability relies on the vessel being submerged, how on earth do you handle intense control across pitch, roll, and yaw?
This is where we see the most significant evolution in hydrofoil design over the last, say, 50 years. We've moved from these simple, robust, passive systems to hyper-complex, active ones that are basically flying computers.
Okay, let's start with the older method, passive stability through what are called surface-piercing foils.
Passive systems are beautiful in their mechanical simplicity. They often use V-shaped or dihedral foils that actually cut across the water surface.
So part of the foil is in the air, part is in the water.
Correct. And they rely on a self-regulating feedback loop. If a wave, for instance, causes the boat to rise too high, less of that V-shaped foil is submerged in the water.
Which means less lifting surface.
Exactly. Since less foil is submerged, the total lifting surface area decreases. The lift plummets, and the boat naturally settles back down to its designated height. It's purely mechanical.
No computer needed.
No computer, no complicated hydraulics. It made it absolutely ideal for those early commercial vessels. Robust and reliable.
But the truly modern, high-performance, high-efficiency systems, like the ones we see in the America's Cup or these new electric ferries, they use active stability with fully submerged foils. This is where the machine really starts borrowing from the aerospace industry.
Yeah, active stability is required because fully submerged foils, while they offer the maximum efficiency and speed, They possess absolutely zero inherent mechanical stability.
They're flying blind.
They're effectively flying blind. Therefore, they demand these sophisticated real-time control systems. We're talking about a miniaturized flight computer that is taking hundreds of measurements every single second.
What exactly is that flight computer measuring? I mean, it's not just a fancy autopilot, is it?
Oh, far from it. It's a fully integrated sensory array. It's using accelerometers and gyroscopes to track the boat's pitch, roll, and yaw. It's using GPS and inertial measurement units, IMUs, to track velocity and orientation.
And crucially, it has to know what's coming.
Critically, yes. It uses sonar or radar, sometimes both, to determine the precise height above the water and, more importantly, to predict the incoming swell. The AI flight computer then governs these adjustable wing flaps, or sometimes the entire foil, making micro-corrections hundreds and hundreds of times every second.
So it sounds less like a boat and more like a drone that never quite leaves the water's surface.
That's the perfect way to describe it. Modern electric hydrofoils, like the Candela C8 that our sources mention, they rely on this auto-stabilizing flight software to constantly adjust the angle of attack and the lift profile. And this is why these vessels can genuinely glide across rough water as if it were glass, maintaining a level platform regardless of the waves passing underneath.
Yet, even with all that incredible technology, instability issues can still plague these systems. The sources highlight things like porpoising, ventilation, and of course the inevitable speed ceiling.
Porpoising is a nasty one. It's a severe vertical oscillation, this rapid rhythmic up and down motion that's not only dangerous and uncomfortable, but it wastes a ton of energy. It typically happens when the control loop overcorrects, or when the center of lift shifts too far forward or back.
And ventilation, you mentioned, is when air gets sucked down onto the foils. That sounds even worse.
It is arguably worse. If the water surface is chaotic, air can be sucked right down the struts that connect the foil to the hull. Air is, as we said, about 800 times less dense than water. So when a section of the foil suddenly becomes enveloped in an air bubble,
Lift just disappears.
it immediately loses a massive amount of lift, causing a sudden hard stall, or what pilots call a ventilation crash. Active systems have to use incredibly precise trim and highly optimized strut shapes to prevent this from happening.
And then there's the final physics hurdle, the one that limited the speed of military hydrofoils for decades. The speed ceiling introduced by cavitation.
Cavitation is the universal speed limit for pretty much any object moving underwater. It typically starts to occur around 40 to 50 knots.
And what's actually happening there?
Well, remember Bernoulli's principle. As the water rushes over that low-pressure upper surface of the foil, the pressure can drop so low that the water actually vaporizes at ambient temperature. It boils without heat.
So it turns into tiny steam bubbles.
Exactly. Tiny steam bubbles or cavities. So now the boat is effectively running through a mix of water and steam.
And that vapor contact causes, what, 3 massive problems?
At least 3. First, you get a huge loss of lift because the foil is no longer running through dense water. Second, you get terrible vibration and noise. And third, and critically, you get rapid erosion.
Erosion from water vapor.
When those vapor bubbles collapse under high pressure, they create these microjets of water that hammer the surface of the foil with incredible force. They can destroy stainless steel and even high-strength alloys over time. It literally limits the lifespan and the performance of the vessel.
So if cavitation is this hard physical barrier, then the exotic solution reserved for, high-end military and research craft is something called supercavitation.
Right.
So you're saying the solution to the speed problem is to intentionally turn the water into steam, so the vessel is essentially flying through a stable gas bubble instead of liquid.
That is precisely the counterintuitive genius of supercavitation. It doesn't try to defeat the problem, it exploits it. Engineers design a foil, which is usually a complex wedge shape rather than a classic airplane profile, to intentionally create a stable, massive vapor cavity that completely envelops the entire foil structure.
So the foil is wrapped in this gas bubble.
It is. So it's no longer running through dense water, it's running through thin vapor.
And if you're flying through vapor, your water friction essentially disappears.
It drops precipitously. This allows for speeds well beyond 100 knots, potentially even up to 200 knots. However, it's incredibly hard to maintain.
I can imagine.
You need complex systems to pump gas, often engine exhaust, into the cavity just to keep it stable. And you sacrifice all of your low-speed maneuverability and stability. Our sources confirm this technology is primarily restricted to specialized military torpedoes and research craft, but it just demonstrates the human ingenuity in pushing the absolute limits of hydrodynamics.
That beautifully lays out the demanding physics of flight on water. It's just astonishing that inventors were attempting this 150 years ago without AI flight computers or high-strength carbon fiber.
Without any of it.
So now let's transition from the modern physics lab to the early workshops of the late 19th and early 20th centuries. To appreciate how far we've come, we really have to trace the genesis of this incredible machine, starting way, way back in 1869.
The conceptual seed was planted deep in the Victorian era. The very first recorded concept belongs to a French engineer, Emmanuel Denis Farcaud, in 1869. He patented designs for a rowing boat equipped with these simple wedge-shaped foils.
A rowing boat, so he was trying to make manual labor easier.
Exactly. It was primitive, but Farcaud was the first person to realize that if you had inclined planes moving through water, they could generate enough upward force to lift the hull and reduce resistance. He was just trying to eliminate the sheer back-breaking effort of rowing a heavy vessel through the water.
So Farcaud may have planted the seed, but the first documented success belongs to an Italian, Enrico Forlani, who took a much more radical approach.
Forlani was an astonishingly prolific inventor. He was working on everything from early aviation to helicopters. He began his hydrofoil experiments around 1898, and he developed this design called the ladder foil system.
A ladder, what does that mean?
It was literally stacks of small, vertically arranged foils. The system offered great stability and a lot of lift at slower speeds. And his big breakthrough arrived in 1906 on Lake Maggiore.
What happened there?
Using an air screw-driven prototype, so a propeller spinning in the air, not the water, he achieved a historic speed of 36.9 knots, which is about 68 kilometers per hour. That was the moment the hydrofoil transitioned from a theory on paper to a reality on the water.
And to put that into perspective, in 1906, that speed was almost unheard of for any kind of marine vessel. It was the equivalent of a modern breakthrough in speed travel.
Oh, absolutely. Traditional steamships were crawling along at maybe 15 to 20 knots. Forlani nearly doubled the speed potential using only moderate engine power, simply by getting that hull out of the water. This triggered a global race to defeat water drag.
And we saw secondary efforts almost immediately. I see John Isaac Thornycroft, known for his torpedo boats, built the Miranda III in Britain in 1909. In France, Comte Charles de Lambert was experimenting with variable pitch fins on the Seine in 1904.
A lot of experimentation.
But the race was about to be dominated, at least for a time, by the most famous man on Earth, Alexander Graham Bell.
It's just so often forgotten that the man who invented the telephone then essentially decided, you know what, water's too slow. That transition from acoustics and electrical communication to hydrodynamics is just a fascinating side journey in his life.
So Bell, along with his chief engineer Casey Baldwin, began their experiments in Nova Scotia starting in 1908, and they were directly inspired by Forlani.
They were. They heard the news of Forlani's success and got to work.
And what drove this pivot? Was it just pure curiosity, or was there a practical objective behind it?
I think it was a combination. Bell was deeply, deeply interested in anything that could revolutionize transportation. He saw the inherent drag limitation of displacement hulls as this fundamental barrier to progress. His team was incredibly rigorous. They built several prototypes, they iterated on Forlani's ladder concept, but they applied immense scientific discipline to the angles and the materials they were using.
Their efforts culminated in the HD4 in 1919, and this was a serious piece of engineering for its time.
It was a Leviathan. It was a 5-ton vessel powered by 2 massive 350-horsepower Renault aircraft engines, the very best available at the close of World War I. They optimized the foil system heavily, focusing on that surface-piercing design for stability.
And the results?
The HD4 achieved a triumph that stunned the world. It set a world marine speed record of 114 kilometers, or 62 knots.
62 knots. In 1919, that record stood unchallenged for 2 whole decades. It really transitioned the hydrofoil from this curious invention into a genuine blueprint for high-speed marine transit.
It did.
But if the technology was so fast and so efficient, why did it take until the 1950s for it to become a commercial reality?
That's a crucial historical question.
Yeah.
Speed was proven, yes, but the key issues were stability, manufacturing complexity, and engine reliability. Building 5-ton hulls and mounting 2 high-performance aircraft engines was incredibly expensive and required constant skilled maintenance. The foils themselves were structurally complex. It just needed industrial-scale refinement.
And that refinement came, as it so often does, from military necessity.
Unfortunately, yes. The 20th century saw that shift from niche invention to strategic asset, the mid-century military age of hydrofoils.
And World War II was the catalyst.
It was the primary catalyst for industrializing the technology. A German engineer named Hans von Schertl developed a series of prototypes for the German military, realizing that the speed potential was ideal for fast attack and mine-laying missions. His VS-6, a 17-ton prototype tested in 1940 and 1941, reached a formidable 47 knots.
After the war, Schertel was instrumental in bringing this technology to the civilian world by relocating to Switzerland and founding a company called Supermar.
And Supermar became the first major global commercial hydrofoil company. Their landmark vessel, which they launched in 1952, was the PT-10 Freccia d'Oro, the Golden Arrow. This was the world's first successful commercial hydrofoil, designed with robust surface-piercing V-foils for that passive stability we talked about.
How many people could it carry?
It carried 32 passengers at 35 knots across Lake Maggiore. This marked the absolute dawn of commercial foiling.
And Supermar's influence wasn't just in Europe. They quickly became the global standard.
They did, because they had solved the core problem of reliability and stability for medium-sized vessels. They licensed their designs globally. Companies like General Dynamics in the USA and Hitachi Shipbuilding in Japan mass-produced Supermar designs. Between 1952 and 1971, Supermar built and licensed over 200 hydrofoils. They essentially set the standard for fast coastal transit for decades.
And at the same time, on the other side of the Iron Curtain, the Soviet Union was building its own hydrofoil giant, driven by the truly visionary engineer Rostislav Alexeyev. He's often called the father of modern hydrofoils.
Alexeyev recognized the unique advantages of hydrofoils for the USSR's massive interconnected network of rivers and inland waterways. His designs weren't focused on military stealth at first, but on mass transit and, critically, reliability. He launched the Raketa riverboat in 1957, which was not just a prototype, but the first truly mass-produced hydrofoil in history.
Why did Alexeyev's design take off so dramatically on inland waterways compared to the Western coastal approach?
The need was just acute. The USSR had these vast distances and often very poor road infrastructure between cities that were connected by major rivers like the Volga. A traditional displacement boat was far too slow. A plane was too expensive.
So it filled a perfect niche.
A perfect niche. Alexeyev's hydrofoils, and they were followed by the even more famous Meteor and Voskhod models, were cheap, they were highly reliable, and they allowed for rapid, comfortable transit on rivers. They essentially gave the USSR a crucial internal transportation advantage. By the 1980s, the Soviet Union operated the largest hydrofoil fleet in the entire world, carrying millions of passengers every year.
Alexeyev also pushed the boundary with his extreme vision. He pioneered the Ekranoplans, those monstrous ground effect vehicles.
He did. The Ekranoplan was an attempt to just blur the line between ships and aircraft entirely, flying just meters above the water surface using a high-pressure air cushion generated by massive engines.
So not a hydrofoil, but related in spirit.
Exactly. While technically not a hydrofoil, it just shows Alexeyev's deep commitment to using fluid dynamics to defeat drag and achieve incredible speed, whether it was in the water or just above it.
And the Cold War military race was heating up globally, driven by that same quest for speed and surprise.
The U.S. Navy started serious research in the mid-1950s, building increasingly ambitious prototypes. We saw vessels like the Halibades and, notably, the Canadian test vessel, the HMCS Bras d'Or, which was capable of reaching an incredible 63 knots in the late 1960s.
And the goal?
The goal was to deploy these fast patrol craft that could intercept conventional destroyers or subs without being detected until it was way too late.
Wait, if the stability systems in the drag were so complex, how did these massive military vessels maintain that speed and control in rough ocean conditions?
This is where the military had to push active stability systems far ahead of the commercial market. They were the first to integrate early electronic sensors and rudimentary flight computers just to manage the trim. The sheer power required was also immense. They often used water jet propulsion to overcome the drag and maintain speed above that critical cavitation threshold for as long as possible.
So let's talk about some of the key military platforms that were deployed.
The adoption was global. The USSR deployed its Turia torpedo boats and Matka missile hydrofoils. The USA had its Pegasus-class patrol hydrofoils, which were active from 1977 to 1993, specifically designed for rapid coastal defense and anti-shipping roles. Italy's Sparviero-class fast attack craft also operated on foils, reaching 50 knots.
So these were serious vessels.
Very serious vessels, built entirely around the concept of unmatched speed and surprise attack.
But the sources all remind us they all hit that same inescapable technical wall: cavitation.
That's the painful truth. That speed barrier of around 40–50 knots, where the vapor bubbles start destroying the foil surfaces, meant that while hydrofoils were fast, they couldn't quite achieve the sustained, ocean-going, high-speed performance their designers really hoped for without constant, very expensive maintenance. This physical constraint meant military adoption was widespread but eventually limited. It was waiting for the material and computing science leaps of the 21st century to truly be overcome.
Which brings us perfectly to the modern era, where new materials and new propulsion technologies have fueled this global renaissance.
Yes, the late 20th and early 21st centuries finally delivered the tools that the engineers in the 1950s desperately needed. We saw the advent of modern materials, incredibly light and strong carbon fiber composites, high-strength, corrosion-resistant alloys. This allowed engineers to design and produce these complex, previously impossible foil shapes, V-shapes, C-shapes, S-shapes, even Z-shaped foils for superior control and stability in rough seas.
And the sporting world immediately adopted this technology and pushed its limits to the absolute extreme.
The sporting revolution was basically a public test lab. We saw the development of foiling surfboards, powered e-foils from companies like Liftfoils, making water flight accessible to individuals for the first time. But the ultimate showcase, the real technology accelerator, was the America's Cup.
How did the America's Cup fundamentally change the game for commercial hydrofoils?
It forced this rapid, multi-million-dollar refinement of active stabilization systems. The AC-72 catamarans that were foiling back in 2013 were shocking to watch. The AC-75 monohulls in 2021 were hyper-optimized. They were constantly making hundreds of adjustments per second just to maintain flight, even during high-speed maneuvers.
And that's not just for show.
No, the real-time sensor data, the hydraulic systems, the flight control logic that was developed for the AC-75 that is directly transferring to the new generation of commercial ferries and yachts today.
But the most significant leap, the convergence that changes the game entirely and brings us to the future, is the marriage of hydrofoils and electric propulsion. Why is this marriage so crucial?
It all comes down to simple arithmetic dictated by efficiency. Electric boats have traditionally struggled with two major factors: battery weight and the massive drag of a displacement hull.
Right, it's a vicious cycle.
It is. Batteries are heavy, and the more power you need to overcome drag, the more batteries you need, which makes the boat heavier, which requires more power. But because foils reduce drag by up to 80 to 90%, electric propulsion suddenly becomes viable. You need less than a quarter of the battery mass to achieve the same speed and range as a conventional electric displacement boat.
So it transitions electric boats from being a niche short-range experiment into a realistic long-range mass transit solution.
Exactly. That is why companies like Candela in Sweden and Navier in the US are now building these advanced electric hydrofoils. The technology is finally mature enough to deliver on the promise.
Let's focus on one of those key players, like the Candela C8, to really understand the current state of the art.
The Candela C8 and their larger P-series ferries, they really embody this convergence. They use these carbon titanium wings and advanced auto-stabilizing flight software running on the same kind of logic you'd find in drone avionics to just glide across rough water effortlessly.
And the benefits are huge.
They deliver near-silent propulsion, which is key for urban waterways. And crucially, they produce almost no wake, which solves a massive problem of shoreline erosion in crowded harbors and canals. This is no longer just an improvement, it's a fundamental transformation of maritime travel.
We also see smaller, more personalized examples of this convergence, which shows how broadly the technology is being applied.
Yes, the market is diversifying very rapidly. You have the Quadrifoil Q2, which is an all-electric two-seater personal craft. And perhaps the most novel, the Manta 5 Hydrofoiler XE1, which is essentially the electric bike of the water.
An e-bike for the water.
It's a cycling frame mounted on hydrofoils, allowing human pedal power, augmented by a small electric motor, to achieve lift. This just demonstrates that the efficiency gain is so high, a single human being can sustain foiling flight.
That sets the stage for a dramatic shift. So let's move to part 4, which is crucial for our listener, the learner, positioning the hydrofoil against its competitors. We need to understand exactly where it fits in the marine ecosystem by comparing it to the rest of the fleet.
Right, because water transportation is a very diverse landscape, and it's all defined by fundamental physics. We have 5 main players to consider: hydrofoils, catamarans, conventional displacement ferries, hovercrafts, and seaplanes. Each one conquers the water using a radically different approach.
Okay, let's start the head-to-head on speed. Who wins on pure velocity?
On the water surface, the hydrofoils and hovercrafts dominate. They both typically hit that 30 to 60 plus miles per hour range, and they're limited mainly by the sea state and the stress tolerances of their components.
But if you include the seaplane?
The context changes entirely. Seaplanes are aircraft. They operate at aviation scale speeds of 150 to 220 miles per hour. Now that speed comes with aviation-grade costs and energy demands, but they are clearly the fastest way to move over water, period.
Okay, now for the critical comparison, energy efficiency, especially in the context of sustainability. This is where the hydrofoil really shines. Let's get the ranking right.
This is the hydrofoils winning category, hands down. Hydrofoils are the most efficient because of that near elimination of wave drag and the viability of electric options. Catamarans are a solid second, thanks to their slender, efficient dual-hull geometry, which reduces wave drag compared to a single displacement hull.
In conventional ferries.
They're mid-efficiency, but the interesting outlier here is the hovercraft, which we flagged in the critique as having bad efficiency.
Right. Why does something that flies on air use so much power?
Because the core technology, pushing massive volumes of air downward to create and maintain that lifting cushion, is incredibly energy-intensive. Air is voluminous and diffuse. You have to move tremendous quantities of it very quickly, which requires powerful, continuous running fans and enormous engines.
So while it's fast.
While the hovercraft is fast and highly versatile in terms of sheer cost per mile efficiency, the hydrofoil dramatically outperforms it by using dense water for lift, which requires far, far less energy volume to generate the necessary force.
Okay, let's move to ride quality, the comfort factor. If you're building a sustainable future of mass transit, ride quality is absolutely essential to attract commuters.
And this is the hydrofoil's other defining advantage.
Yeah.
Because it literally rises above the waves, it delivers the smoothest possible ride. In choppy water, the modern hydrofoil ride is rated as excellent.
And the others?
The catamaran is good. It manages rough water well because of its stability. The traditional ferry is, okay, but it's subject to significant roll. And the hovercraft ride is often rated as poor.
Why poor?
Because of the constant rapid skirt slapping against the wave peaks. It makes for a very jarring, bumpy experience.
And related to comfort, there's the noise factor and motion sickness.
Hydrofoils, especially when they're electric, are very low noise. Hovercrafts, because of the constant churn of those massive air fans, are inherently high noise, which also limits their operational hours in environmentally sensitive harbors. And crucially, for anyone who gets seasick,
This is important.
the hydrofoil score is very, very low on motion sickness risk because it remains stable, level, and separated from the swell. If you are prone to seasickness, the hydrofoil is your best friend on the water.
Now for the trade-offs, which are equally important for the learner, hydrofoils are fast and smooth, but what about stability and the risks of operation?
Inherent stability is complex. A catamaran offers natural, passive stability just due to its wide beam. Modern hydrofoils offer highly stable rides, but that stability is managed by complex software control systems. That introduces a reliance on technology.
And the main operational vulnerability for hydrofoils is debris strikes.
Absolutely.
Yeah.
Hitting logs, ropes, or even large clumps of floating seaweed can severely damage a slender foil system or cause a sudden catastrophic loss of flight. This necessitates having highly clear, well-maintained transit corridors.
And terrain versatility is where the hydrofoil shows its starkest limitation.
Yes, hydrofoils are limited to deep, relatively clean water. They cannot operate in shallow estuaries, nor can they transition to land. This is the realm where the hovercrafts and seaplanes are the unmatched winners. The hovercraft is truly all-terrain. It can conquer land, water, ice, mud, and sand. The hydrofoil has to stick to its clear, deep, marine transit corridors, which limits its utility in certain geographical zones.
Finally, capacity and cost. Hydrofoils are high-speed premium vessels, but they're not bulk carriers.
No, their capacity remains small to medium. They typically serve anywhere from 6 to 300 passengers. The conventional displacement ferry remains the undisputed king of bulk transport. It's capable of moving vehicles, massive freight, and thousands of people.
And in terms of sheer capital cost,
Catamarans are often the simplest, most reliable, and most cost-effective to operate and maintain. Hovercrafts and seaplanes are the most expensive due to their complex systems and high-grade maintenance requirements. Hydrofoils are fuel-efficient, but they demand skilled labor and high material costs for their complex foil systems and flight computers.
So if we synthesize all this data, the final winners in our competitive matrix really define the niches of the future.
They do. If you need water speed, energy efficiency, unmatched comfort, or zero-emission sustainability, The hydrofoil wins.
But if you need massive cargo capacity,
And cheap, high-volume transport, you take the conventional ferry. If you need all-terrain versatility and military stealth capability, use the hovercraft. And if you just need the cheapest, simplest, and most robust mass transit solution, the catamaran remains highly competitive.
so the hydrofoil doesn't replace everything.
No, but it defines the critical niche for fast, clean, and supremely comfortable coastal mobility. The old brute force methods, like the hovercraft, are simply too power-hungry and noisy for a zero-emissions, densely populated urban world.
And that inefficiency is exactly why the hydrofoil is experiencing this incredible renaissance right now as we move into part 5, the modern renaissance and the 2035 revolution.
This shift is driven by the fact that technology has finally caught up with the engineering ambition of those early inventors like Bell and Alexiev. The 21st century's materials science, leaked carbon fiber, titanium alloys, advanced sensor packages allowed for those highly specific V, C, and S-shaped foil designs necessary for stability and control even in large vessels.
And we discussed the sporting revolution, the foiling surfboards, and the America's Cup. That accelerated the development of reliable, active stabilization systems that could make hundreds of corrections per second.
Correct. The constant real-world testing and elite racing means that the control algorithms are now mature enough for commercial applications. A commuter ferry needs the same reliability as an aircraft, and that reliability was proven under the most extreme conditions in the racing world.
And that brings us back to the electric convergence. We established the basic math. Foils cut drag by 70 to 90%, making electric power viable. But what are the long-term implications of this convergence?
The implications are seismic. It means we can finally transition from a linear power source, diesel, to a battery-based power source, electric, without sacrificing performance. Critically, it allows cities to mandate zero-emission ferries without compromising travel times.
So where traditional electric boats offered poor range,
The hydrofoil offers a viable range and speed profile for major commuter routes. It makes electric propulsion not just feasible, but actually superior in performance, cost, and environmental impact.
that's why we see modern companies like Candela and Navier dominating the discussion. They are building real commercial electric hydrofoils right now.
The Candela P series is already operating in places like Stockholm. Their C8 private vessel uses the C-Pod propulsion unit and sophisticated flight software to achieve a range that rivals conventional bass boats while being almost entirely silent and wake-free. These vessels are forcing the market to completely change its expectation of what a boat is. The boat is now a computer that flies just above the water.
Let's talk about the 2035 Great Shift. The prediction is that by 2035, the majority of new small to medium coastal passenger vessels will be electric and foiling. What are the major forces, the policy, economic, and logistical pressures making this shift seem so inevitable?
I'd say 4 major forces are converging globally. First, energy economics. We already established that hydrofoils make electric propulsion superior by dramatically cutting drag. Over the vessel's lifespan, that leads to much lower operating costs compared to heavily taxed, high-maintenance diesel engines.
Second is climate policy.
Cities globally, especially in Europe and Asia, are facing critical mandates for decarbonization and zero emissions. Plus, they're dealing with the worsening consequences of ocean rise and increasing coastal erosion. Moving away from dirty diesel ferries and adopting wake-free, silent hydrofoils becomes an immediate policy win.
Third, urban congestion. This is a huge factor in coastal megacities.
Absolutely. Think of Mumbai or New York or Hong Kong. Land traffic has become completely impossible. The ocean, which has always been there, suddenly becomes a viable high-speed highway to bypass that impossible land congestion. The hydrofoil provides the necessary speed to make water transit actually competitive with rail or road.
And the fourth force is the computing power that finally makes the whole system safe and reliable, computing and autonomy.
The AI flight computers are now mature enough to govern the complex, real-time foil control systems, ensuring unprecedented stability and safety. This combination of forces economic rationale, climate policy pressure, urban necessity, and mature AI is what's relegating traditional displacement hulls to cargo-only roles.
Okay, let's detail the impact on specific urban areas. The rise of foiling ferries and global adoption. If Stockholm mandates a switch to Candela ferries, what are the logistical challenges for their infrastructure?
That's where the real-world implementation gets complex. These are high-speed ferries carrying 40 to 200 passengers. For cities like Stockholm, Venice, Singapore, or Sydney, the challenge isn't the boat, it's the dock. You need to upgrade existing ferry terminals with specialized automated docking stations that can safely handle a vessel arriving at speed that might not be fully displacement.
And charging, that's a huge electrical demand right in the middle of a dense urban environment.
It is. You need dedicated hydrofoil charging docks capable of delivering high-power charging, often 300 to 500 kilowatts, very quickly, especially during peak commute hours. Stockholm, for instance, is pioneering using existing grid infrastructure, but requires intelligent load balancing. Dubai is expected to integrate solar canopies over its hydrofoil docks to offset some of that energy demand. The build-out of this infrastructure is really the main bottleneck for the 2035 prediction.
Now, think of the economic effect this will have on emerging coastal economies like India or the Philippines.
It's transformative. Coastal megacities in India like Mumbai or Chennai can adopt hydrofoil commuter boats as a rapid alternative to gridlocked land transport. In island nations like Indonesia and the Philippines, these vessels become essential inter-island shuttles, leaping over the need for expensive, centralized road infrastructure.
So travel times are cut, wake damage disappears.
Travel times are cut in half, wake damage to sensitive islands disappears, and noise pollution drops dramatically.
So the hydrofoil becomes what electric trains were to 20th century land transit, the backbone of modern mobility infrastructure, but for the water.
It's a perfect analogy. But the future is even more disruptive with the predicted rise of the autonomous hydropods.
This introduces a new, highly scalable class of vessel. Small 2 to 8 seat electric hydrofoils operating like oceanic self-driving taxis. The long-promised Uber on water. What kind of technology makes these possible and, more importantly, safe?
Safety is absolutely paramount for autonomous operation. These hydropods will be summoned via an app. They'll feature AI-driven docking that can perfectly align the vessel even in rough water, and they'll rely heavily on triple redundant collision avoidance systems.
Triple redundant?
Yes. Radar for weather and large ships, LiDAR for close-range obstacle detection like small boats, and high-frequency sonar for underwater debris and swell mapping. They will operate 24/7, leveraging dynamic routing based on real-time swell prediction for maximum efficiency.
And where do we see these autonomous networks developing first?
Closed or semi-closed systems are the logical first steps. The intricate canal zones of Dubai, the resort ecosystems of the Maldives where you have fixed routes and low debris, that's the norm. Or structured environments like San Francisco Bay, where a sophisticated vessel traffic management system is already in place. The cost savings from eliminating human crews, coupled with the efficiency of the vessels, will make them economically unstoppable by 2040.
The military is also predicted to experience a renaissance in the 2030s, turning back to the hydrofoil. Why the return to a system that was limited by cavitation just a few decades ago?
The limiting factor speed has now been mitigated by advances in materials and control systems. The military's need for speed, low drag, and a silent approach is amplified in modern littoral warfare. Navies are transitioning to stealth electric hydrofoil patrol craft.
Because they're electric and wake-free.
They possess a much lower heat signature and acoustic signature, making them ideal for rapid covert insertion or reconnaissance.
And the power of autonomy allows for entirely new naval strategies.
The rise of autonomous hydrofoil swarms, unmanned foiling drones, is a key prediction. These swarms are fast, light, and maneuverable, capable of rapid interception, sub-hunting using towed array sonar, and anti-piracy operations. They are digitally governed, acting in coordination across vast areas, positioning the hydrofoil as the naval equivalent of networked electric fighter jets. Powers like the U.S. Navy, Japan, and Australia are investing heavily in these concepts for rapid maritime domain awareness.
Beyond military and mass transit, the revolution is hitting water sports and even workboats.
Oh, the cultural impact is already visible. Foiling is becoming a global lifestyle sport. Personal foiling watercraft, capable of 30 to 40 knots on battery power, are replacing traditional gas-guzzling runabouts. We'll also see specialized commercial hydrofoil workboats and cargo craft.
What kind of workboats specifically benefit from foiling?
Think about rescue craft that need to get to an emergency scene faster than any other vessel, or electric hydrofoil pilot boats used to guide massive tankers, or foil-stabilized offshore support vessels that need to maintain a stable platform for sensitive maintenance work. For cargo, hydrofoils fill a crucial logistics niche, carrying light, high-value freight like pharmaceuticals, high-tech components, or emergency supplies for remote islands, offering high-speed and clean operation where planes are too expensive and ships are too slow.
The environmental impact of this shift is profound and multifaceted. It extends far beyond just replacing diesel with batteries.
The ecological benefits are enormous. Near-zero wake is critical. Traditional boat wakes cause massive shoreline erosion, damaging coastal wetlands and mangrove ecosystems. By skimming above the water, Hydrofoils eliminate this damage, allowing these sensitive coastal zones to recover.
And the quiet movement.
Quiet movement is safer for marine mammals. It significantly reduces noise pollution and the risk of propeller strikes. And the ultra-efficient energy use means not only low emissions, but also less strain on power grids. Hydrofoils are rightly considered the gold standard for sustainable marine mobility by 2035.
And the economics of this transition are projected to hit a tipping point pretty soon.
By 2035, the combination of plummeting battery costs, mass production of advanced carbon composites, and the elimination of crew costs due to autonomy means that a diesel ferry will cost significantly more per passenger mile to operate than an electric hydrofoil. The hydrofoil transitions from being the expensive, exotic environmental choice to being the rational economic choice for transportation investors worldwide.
This necessitates deep integration into the urban plan, the concept of the smart coastal city.
Absolutely. Cities cannot just bolt these systems onto old infrastructure. They will develop dedicated marine transit corridors for foiling ferries, install sophisticated hydrofoil charging docks and auto-docking stations, and utilize digital twin ocean models to predict swell and optimally route vessels. Hydrofoils become as normalized and integrated as rail lines or metro systems are today.
That paints a vivid picture of the near future. Now let's push beyond 2035 and enter the truly speculative terrain of Part 6, the hydrofoil futures of 2050 and 2100. The sources here posit that in the face of major challenges like rising sea levels, humanity will adapt not by resisting the ocean, but by learning to ride the tide.
By 2050, the very concept of a coastal city fundamentally changes. The sources posit that coastal megacities will become cities of canals. The hydrofoil ceases to be a novelty and becomes the defining machine of this new era, the aeromarine network.
So imagine these vast electric hydrofoil networks stitching together entirely new coastal megaregions.
Think of interconnected urban belts, not connected by roads, but by AI-guided hydrofoil shuttles, sometimes called aeromarines, skimming the water at 120 kilometers per hour. They're covered in photovoltaic scales, allowing them to capture solar energy, and they are essentially silent. The Mumbai Maritime Corridor or a vast Los Francis mega corridor become everyday realities.
And the concept of the foil commons speaks to the integration of this technology into public protected infrastructure.
It suggests vast protected public transit corridors on the open water, all guided by the ocean mesh, a decentralized sensor-driven network that updates currents, monitors debris, and tracks marine life movements in real time. The seas have become smart highways, where the silent, wake-free movement of hydrofoils actually allows marine wildlife to coexist and thrive, with automated systems diverting around whale migration paths.
This sounds almost entirely automated. What happens to the human element in all this?
Humans become the system monitors and designers. The need to police this new, fluid frontier gives rise to the ocean rangers. With floating borders and shifting sovereignty due to sea level rise, navies deploy autonomous hydrofoil rangers. Stealthy, long-range electric craft operating as silent, swift swarms. Their role is coastal security, search and rescue, and environmental enforcement. Their motto is indeed compelling. Where land ends, we begin.
Then we get into the highly conceptual stuff, the skyfoils. How do you use a hydrofoil to sail through the air like a skipping stone?
This pushes the concept to its absolute technical limit. By the mid-2040s, engineers explore hybrid systems that briefly launch small craft above the waterline for short durations, leveraging a combination of hydrolift and high-velocity aerolift. They are not sustained aircraft.
They're just skipping.
They're using the hydrofoil concept, generating massive initial speed and lift to briefly skip across the surface tension of the air-water interface for several kilometers at super high speed, significantly cutting transit time over open water. It's an ultra-fast, short-hop technology.
And the cultural impact is also dramatic with the rise of hydrofoil surf cities.
Entire subcultures form around deep foiling, using AI-stabilized foils to glide miles offshore, unhindered by coastal swells or currents. These eventually evolve into full-blown floating communities, archipelagos of stable foil-assisted platforms. The hydrofoil ceases to be just a transport machine. It becomes an extension of the human body, facilitating a completely new, integrated relationship with the water, far removed from the shore.
That's 2050. Let's leap forward another 50 years to 2100 and the age of the offland people living in these floating cities called pelagians.
By 2100, nearly 1 billion people live on or above the ocean in massive, stable, floating settlements. The hydrofoils that serve them have evolved into almost sentient entities. We see the hydrocells vessels built with advanced bio-inspired sensors and neurofluid processors that allow them to self-learn and adapt their foil geometry on the fly. They literally remember every journey, every swell pattern, and every encounter with debris, blurring the line between machine and organism.
Why neurofluid processors? What advantage do they offer over conventional silicon chips?
The source material suggests that neurofluidics allows for seamless, instantaneous changes in material density and shape. Conventional materials are rigid and slow to adapt. Neurofluidics enables the vessel to adapt its foil angle, shape, and even surface texture hundreds of times faster than hydraulic systems, providing perfect intuitive stability. It makes the vessel feel almost telepathic in its response to the water.
This sounds entirely biomimetic. Tell me about the organic foils.
The source mentions the discovery of organic foils by a future Japanese Kenyan ocean lab. These foils are inspired by whale flukes and manta ray wing patterns. By 2100, these self-healing biomimetic foils have replaced 90% of rigid systems. They are built from smart composite materials that can repair microfractures, change color based on water quality, and whisper pressure data like an animal sensing a storm. They are lovingly called the living wings.
And the main transit between these massive floating cities, Leviathan-class hydrofoils.
These are cathedral-like vessels designed for interpelagian transit. Imagine a ship 300 meters long, riding 5 meters above the surface at 300 kilometers per hour. They are capable of diving briefly beneath chaotic superstorms, utilizing their robust foil structures for temporary submerged stabilization. They are civilization-scale transportation hubs, complete with internal vertical farms and salt-to-fresh conversion engines. The journey itself is a transformational cultural experience, not just a commute.
And the military component also evolves into the aeropelagial defense web.
With vast maritime federations replacing traditional nation-states, autonomous hydrofoil guardians operating in vast, interconnected swarms patrol illegal zones and rogue, drifting megacities. They are nano-coated for radar absorption, and they communicate strategies across a quantum mesh, operating as the ghost birds of naval warfare. Silent, swift, and omnipresent.
But the most fascinating contradiction comes in the most advanced hydrofoils of 2100. They are also amphibious walkers.
This addresses the ultimate limitation of the traditional hydrofoil: the need for deep water and stable harbors. By 2100, they use a blend of hydrofoil lift and articulating exoskeletal legs. This allows them to glide on water, but also stride across tidal plains, climb sea walls, and anchor themselves securely during the massive storms that characterize the 22nd century. They combine the elegance of high-speed lift with the necessity of anchoring and stability in an unpredictable world.
And finally, we reach the conclusion of this vast speculative journey, the enduring myth of the ghost foil.
It's a powerful mythic symbol for an oceanic civilization. The ghost foil is rumored to be an unregistered, perfectly silent, autonomous hydrofoil roaming the seas, evading all scanners. The whispers suggest it is a self-learning sentinel that carries the memories of every human lost to the waters over 2 centuries. It symbolizes the complete technological and cultural integration of humanity and the ocean. It's the ocean's memory, gliding just above the surface.
Whether we look at the pragmatic, profitable world of 2035 or the mythic, biomimetic future of 2100, the hydrofoil represents a machine that allows humanity to move with the water, not against it.
That is the ultimate synthesis. The hydrofoil has transformed from a 19th century dream and a 20th century military asset into a 21st century environmental and economic necessity. It's not just about raw speed, it's about using finesse and physics, Bernoulli's principle, Newton's law, and AI flight control to elevate the vessel and defy drag with surgical precision.
So for you, the learner, the final takeaway is this. What was once niche, complex engineering is now rapidly becoming a mainstream rational choice for mobility worldwide. Hydrofoils are actively transforming coastal travel, turning the ocean into a viable, clean, incredibly fast, and quiet transportation network.
And our sources posit a deeply provocative closing thought that frames the entire impact of this technology. Hydrofoils may become to oceanic civilization what railroads were to continental expansion, the enabling silent infrastructure of a new fluid frontier.
Think about that for a moment. What societal and economic changes are enabled when 71% of the planet, the ocean, becomes an accessible, high-speed, silent, and sustainable network? We're not just building better boats, we're redefining what a water-based civilization looks like and taking our first true flight across the sea.
We're learning to fly just a few feet above the waves.